Hello, my name is Dana Yu, and this is a presentation for Chemwiki Exercise 3, Problem 5.14, for Professor Larson's class at the University of California, Davis. Problem 5.14, Part A asks, use crystal field theory to draw the electron structure of hexafluorocobaltate 3 ion in a weak field. Part B asks, determine whether tetra-aqua copper 2 ion is paramagnetic or diamagnetic. Please note that I'm going to include a link to the problem in the comment section below. The first thing we want to do is identify what our transition metal complex is. In this case, we have hexafluorocobaltate 3. Looking at the charge on the overall complex, we identify that there's a 3- charge. Knowing that the fluoroion has a -1 charge, we now need to find what the oxidation state of cobalt is. Doing some simple algebra, we find that the oxidation state of copper is 3+. Now we want to go ahead and write the electron configuration for neutral cobalt. We find that it has an electron configuration of 4s2 3d7. Recall this is a transition metal, so it is more energetically favorable to remove electrons from a lower energy orbital first. We therefore remove the electrons from the 4s and 3d orbitals, leaving us with 3d6. We can go ahead and write out the electron configuration for cobalt 3+, and it looks something like this. You may be tempted to stop here, but unfortunately we're not done. Because this is a transition metal complex, there are a few things we must consider. First of all, ligand strength, because it's going to determine the amount of splitting energy and whether pairing electrons is going to be energetically favorable. In order to pair, pairing energy must be less than splitting energy. Also, we must address the molecular geometry of the complex using VSEPR theory. Again, we look at our coordination complex. We have a metal center of cobalt 3+ and 6 fluoroligands surrounding that cobalt. Looking at a ligand field strength chart, we find that our fluoroligand is actually relatively weak. What this means is it's going to produce low splitting energy, so the complex will have minimal electron pairing, because splitting energy is going to be less than pairing energy. Now we need to consider the geometry of the complex. We know that it has an MX6 geometry, which makes it octahedral. This gives us all of the information we need to propose the final electron configuration for this coordination complex. Again, looking at the electron configuration, we have 6d electrons. Those are placed into our 5d orbitals. And now that we know it's an octahedral geometry, we can set up our electron configuration as such, with a degenerate lower and higher orbitals. Placing these 6 electrons in these orbitals, keeping in mind that we're minimizing pairing, we find that all electrons stand alone in their respective orbitals except for one pair. In conclusion, we can say that the fluoroligand is a weak ligand. It will produce a high-spin complex that is typically paramagnetic, and this is because pairing energy is greater than splitting energy, so it is more energetically favorable to promote an electron to a higher energy orbital than it is to pair electrons in the same orbital. Now we turn our attention to tetra-aqua copper 2 to see whether it is paramagnetic or diamagnetic. First, we look at the overall charge on the complex and find that it is 2+. The oxidation state of the aqua ligand is 0, so now we need to find the oxidation state of copper. Doing basic algebra, we find that the oxidation state of copper is 2+. We go ahead and write the electron configuration for neutral copper, and we find that it is 4s2 3d9. Removing 2 electrons from the 4s orbital, it leaves us with an electron configuration of 3d9. Placing these 9 electrons in the 5d orbitals, we find that there is one left over that is unpaired. This means that copper 2+ is paramagnetic, because it has at least one unpaired electron in its d orbital. I hope this presentation was helpful. Please find a link to the problem in the comment section below. Thank you, and have a great day.